Okay, test test. Okay, I think everything is turned on. Just double check the sound. Okay, great. Okay, so so today is the third seminar for this module of generative AI theory and practice. So I think the key thing to take note is that when we talk about generative AI, actually one of the very big topics about generative AI will be covered for today. So you don't see any keywords on the slides, but the big thing that you will be learning for today will be this concept called neural networks. This concept called neural networks. Okay, so so this agenda, you can see there's a strikeout that's optional in the point number 3 of AGI. It's because last batch was about there was this small topic here lah. But I think there is too much to cover for today, so there's too many different things to cover for today. So if we can't finish for today, then I will keep it a little for next week lah. Okay, so traditionally, we are doing this thing called the neural networks, and the neural networks usually spend maybe 6 weeks to learn it, like learn a big part of what neural networks are, lah. And that's after you have done machine learning. But since most of you may not have done machine learning before, so it may be a bit of a stretch. So most of the things, I'll show you code samples as well, because learning about the algorithm neural networks, that is the fundamental of generative AI, fundamental of ChatGPT per se. It's not something that you can learn within 3 hours or 5 hours lah. I mean, like this week and next week. Okay, so just to let you know, this my opinion is that this week's seminar is the most valuable of the other most valuable compared to the other seminars, because most likely if you are going to train more advanced models, then whatever that you learn today for neural networks, you will use it as well lah. Okay, so that's just the flow for today. But before that, let's think about this thing called natural language processing pipeline, or in other words, a pipeline of how you can process data and then train a model and then know whether your model is good lah. So if you look all the way on the top left, it says corpus, right? So corpus is your data set, meaning how many documents, or meaning what kind of text files that you want to be able to use to train the model lah. So in the case of ChatGPT, or in case of so in case of ChatGPT, a corpus of data that exists for that model is that it uses a lot of online data sets lah. So it will crawl. There's crawling data sets whereby, or it will people have extracted data online, and then they're using that data to train lah. And that is why a bit of a side note is that so GPT-2 before GPT-3, so GPT-3/3.5 was when the commercial ChatGPT was very good. But GPT-2 was when I was experimenting with GPT-2 lah, before GPT-3 or 3.5, it was a chatbot that gave a lot of negative responses. So, if you imagine the internet data set, a lot of the data sets are sometimes can be a bit not very friendly lah because people are anonymous online. So training on just a data set that is purely generated by people may not have very good outcomes lah. So if you want to search GPT-2, you can download it off Hugging Face as well to use it lah. Okay, so but that is a huge mouthful. Additional things for you to take note. But your corpus, for example, we always use our data sets. Then the tokenization, you get vocabulary, which is what are the unique words when you extract the tokens from the corpus, and then you do some pre-processing. I don't think we are covering pre-processing in this module. Doesn't seem to be so. But today I'll show you a bit of the pre-processing because the pipeline is something you roughly have to know lah. Okay, and then selection of model because there's a lot of models. So for example, the models that you use was a lot of the probabilistic models. Last week was the byte pair encoder model lah. Yeah, and when you need a model, you train the model. So popular things that most people know that you have a data set. You need to do stuff to the data set, make it clean. Then you train it using a model, and then after that, with the model, you can come up with inference, which is what is it going to predict. So model can predict the score, which is score or generate the next word or similarity. These are quite similar lah. But think of it if you have a movie data set. So one of the common data sets that is being used to teach, if not start with learning data analytics is with the IMDb dataset. So IMDb dataset is a movie dataset lah. So the movie dataset is like you have statements whether this movie is good, and then it will have a score at the end, meaning that if the reviewers say I love this movie a lot, then the score will be close to one. This movie is great, the score will be close to one. I don't like this movie, score will be closer to zero or negative one. So that is what the score can be lah. Similarity is what we learned before. The embeddings is how the model can so the word to vec model, they also determine similarity, how similar words are together lah. Then evaluation will go through 2 weeks from now. So these two are samples or evaluations, but same as how you would train a model, same as how you learn as well. You need to know whether you are learning right or you are not learning right. Okay, where's some? Okay. Sorry, I just saw some messages. Okay, yeah. So, yeah. So based on that, okay. So, but other than that, the slides will be a bit edited because it's just for me to help you understand things better, lah. Okay. So I think I elaborated a bit too much, but let's see a video on NLP, lah. So NLP pipeline, it'll be a lot of things that you have not learned before, but just think of them as the NLP jargon. And with the NLP jargon, that's when you will
Hey everyone, welcome back to the channel. If you're new here,
oh, sorry, that is a bit fast. With the NLP jargon, what that means is that you may gain the vocabulary to learn more about NLP. Don't have to understand everything lah, but understand the concepts within that first.
don't forget to hit that subscribe button. Understands your voice? NLP pipeline. Have you ever wondered how Siri understands your voice? Or how Google Translate works? Or how ChatGPT processes your questions? It all starts with a sophisticated pipeline that transforms raw, messy text into something machines can actually understand. By the end
Okay.
of this,
So just to add on what this person is saying is that I showed you a different pipeline just now lah. So this is a sample pipeline. Pipelines are not necessarily cast in stone, meaning that there's no one specific pipeline that everybody uses. So just bear in mind that there are certain steps and procedures. They are like your tools that those are just tools lah that you need to apply lah. Okay, so this is like a slightly different pipeline. So acquire data, clean data, process data. Sometimes cleaning processing is about the same thing. There's feature engineering, etc. Yeah.
This video, you'll understand every single stage, from raw data to meaningful insights. We'll cover the core stages, look at real code examples, and even explore some advanced techniques. So grab your coffee and let's get started. Let's start at the very beginning, data acquisition. This is where we gather the raw text data that we'll be working with. Data can come from virtually anywhere: social media posts, customer reviews, news articles, medical records, legal documents, or even transcribed speech. The key here is that this data is completely raw and unstructured. Here's a simple example of how we might acquire data using Python. We could scrape a website, read from files, or pull from APIs. In this example, we're reading customer reviews from a CSV file. The important thing to remember is that at this stage, the data is messy. It has typos, emoji, URLs, HTML tags, you name it. That's why we need the next stage. Stage 2 is text cleaning, and trust me, this is where the magic starts to happen. Raw text is like a diamond in the rough. Before we can work with it, we need to clean it up. We're talking about removing HTML tags, URLs, email addresses, special characters, extra white spaces, and yes, even those emoji. Here's what text cleaning looks like in action. We use regular expressions, or regex, to identify and remove unwanted patterns. Look at this before and after example. See how much cleaner the text becomes? We've removed the URL, the HTML tags, and normalized the white space. Now we're ready for the real pre-processing work. Now we enter the heart of the pipeline, text preprocessing. This stage actually has several substages, and each one is crucial. Let's break them down one by one. First up, sentence segmentation. This is where we
Okay.
split paragraphs into
Oh, sorry. So basically, you would have learned some of the categories. Just bear in mind that these other words are quite popular as well, lah. So if you don't know what stemming and lemmatization is, it's okay. May not be gone through for the module, but these are other techniques to clean the data if you have never seen them before.
individual sentences. Now, you might think this is as simple as splitting on periods, but it's actually trickier than that. What about Dr. Smith or USA? We don't want to split there. That's why we use sophisticated tools like NLTK's sentence tokenizer. It understands these.
So NLTK is one of the libraries that is used to split words, lah. So break down the words into its constituent parts, lah. So the tokenizer usually it's from NLTK, but I don't think it's something that is included in your labs. Just something for you to take note if you see more of this processing parts.
These edge cases and segments text intelligently. Next is tokenization, breaking sentences into individual words or tokens. Think of this as breaking down a sentence into its smallest meaningful units. These tokens become the building blocks for everything that follows. Here's how tokenization works in practice. We take a sentence like NLP is amazing and break it into individual tokens. Notice how punctuation can be separated too. That's important for analysis. Lowercasing is simple but powerful. We convert all text to lowercase to ensure consistency. Without this step, Apple, the company, and apple, the fruit, would be treated as completely different words. For most NLP tasks, we want to treat them the same way. One line of code, huge impact on consistency. Now, stop word removal. This is where we filter out the noise. Words like the, is, and, they appear everywhere but don't carry much meaning on their own. Removing them helps us focus on the words that actually matter. Look at this example. After removing stop words, we're left with just the meaningful content words. This reduces dimensionality and improves model performance. One of the most important pre-processing steps, stemming and lemmatization. These techniques reduce words to their base or root form. Running, ran, and runs all get reduced to run. This helps the model understand that these are all related to the same concept. Now, there's a key difference between stemming and lemmatization. Stemming is cruder, it just chops off word endings. Sometimes you get weird results like studi from studies. Lemmatization is smarter. It uses vocabulary and morphological analysis to return the actual root word. Studies become study, a real word. Here's how both work in practice. For most applications, lemmatization gives better results, but stemming is faster. Last but not least, removing digits and punctuation. Depending on your task, numbers and
Okay, so I'll skip the punctuation part because it's
punctuation
quite
and
common sense.
preprocessed strip these characters out. Comes feature engineering, where we convert text into numbers that machine.
Okay, so I think I may not go through the whole pipeline, but you can see popular techniques of feature engineering. You can see the word to vec on here, the back of words here. So these are different techniques to find out. So technically, Ngram is also feature engineering lah. You're trying to decide on what are the patterns that can be continued and it can be still retained lah, in that sense. Okay, and then maybe I'll go to modeling. Maybe I'll go to modeling. Okay. Okay. So just okay lah. Maybe not go through maybe not show you the video, but just know that then after cleaning, you just need to put into your model lah. Okay. So this is a video. If you want to watch it as well, I just send the link into the chat so you can access it to learn a bit more about it. If not, you can search NLP pipeline explained from raw data to feature engineering. Okay, maybe I copy it as well. Okay, so I think because the videos is very succinct and it helps you to learn more about this process lah. And because this process is what all kinds of machine learning engineers will do lah. So what is your data, how to pre-process it, put it inside a specific model, and then there's a similarity score and generations. Okay. Okay, so Gina is saying what is Ngram is like feature engineering. Okay. Let's see, can I write it down somewhere? Let's see. Okay, here we are. Okay, let me try. Okay. So for example, if your corpus, your data set, your original data set is I like to eat pineapple tarts. Okay, so this is your original data. Okay, so what feature engineering does? Let me try drag it. Let me try to make it a bit bigger. So uh, okay. So I like pineapple tarts. Okay. So maybe you like that. Maybe having a lot of that during Chinese New Year. So this is the original data that you train the model on. So what feature engineering is that feature engineering is that you want to there are a few ways to explain it, but the easiest way is that you want to extract the most meaningful information from the original data but yet still retain the meaning lah. Okay, so what is happening is that that's one way to put it, but feature engineering that's not the technical definition. Technical definition is that you want to put features into the model so that the AI model can predict, but you need to choose good features lah. That's the more technical definition lah. But another way to explain it is to extract the most meaningful information from the original data, but yet retain meaning or maybe predictability lah. Okay. So in a sense, what happens is that if you use a bigram, your original data changes to become I like to eat to eat pine apple. Okay. So then what this means is that you can train the model with these features instead. Uh, so of course you can train the model with the original data. It's fine, but feature engineering doesn't mean that your model will necessarily be better. You just need to experiment with it lah. So in the end, if you decide that you want to use this to train the model, then this will be a different set of features for it lor. Yeah. So this part is the feature engineering part lah. You're just selecting the best features to ensure there's predictability lah. Okay. Okay. Hope that makes sense. Okay. Thank you. Thank you, Gina, for the question. Okay, so besides that, let me show you another Kaggle link that you can see. So, if you're not familiar yet, then Kaggle is one of the good tools for you to look at how other people process natural language processing timelines lah. No, pipelines, sorry, pipelines. So as I said, pipelines don't have to be the same. Don't always have to be the same, but they have very similar categories. Yeah, they're just very similar lah. Okay, so the videos pipeline is different from the nodes pipeline. Doesn't really matter. Just accept it as what it is lah. People are just trying to figure out how to make a model that works well. So because of that, that means that there are different ways to do it lah, and that is the art of it lah. Okay, so I sent this Kaggle notebook. It is very comprehensive. I'm not here to go through every single detail, but so you can see, this person that wrote this notebook broke down the pipeline into three main categories. One is text preprocessing, then feature extraction, and then modeling, but of course they are missing the first one, which is gathering the data lah. Okay, so usually there's also gathering of data. Okay, so pipelines are very different lah. They are not necessarily static definitions, but more dynamic in meaning lah. Okay, uh, okay. So I think this one makes a lot of good sense here. So just now in the video, you sort of saw that to prepare text data from different sources, you remove things that are not very useful, like HTML text. If you are scraping the data on a website, you remove the HTML text. You convert them to lowercase and you remove punctuations. You tokenize them. You remove words that are too common, because sometimes the he, she, they, them, these are very common words. And so NLTK has its own stock words library that you can use to remove these words lah. Okay, and then there are other parts. Then you also saw stemming and lemmatization lah. Okay, so the cleaning part, you can always reference and look at this Kaggle notebook. Not here to run through a lot of the notebook, but maybe show you the library. So you see the NLTK is the very common library that people use to do pre-processing and tokenization now. So NLTK, if I'm not wrong, it stands for Natural Language Toolkit lah. Yeah, so you see the stop words here. You can import stop words. So for example, if you do stop words in English, you'll be able to extract all the stop words that somebody has already saved lah. So he, she, they, them should be in this set of data lah. Okay, then there are also other techniques lah, but I don't think we go through this for this module. So additional things for you to look at if you want to try lah. Okay, yeah, additional things for you to look at if you want to try. But as I said, today we're going through quite a bit of things. If I can't really finish all of it, then I'll leave some for next week as well. Okay, so let's go back to this. Okay. Okay, so let's go back to this. Let me move my documents. Okay. Okay, so let's go through a definition of NLP pipeline since I've been talking about that for the past 21 minutes. Okay. The NLP, first of all, you need to know what NLP stands for, right? So the natural language processing pipeline is a systematic sequence of steps designed to something raw, unstructured human language. Okay. So I think when I was doing data, I didn't really at the start I didn't really understand what's the difference between structured and unstructured data lah. So structured data is like your Excel file, or your SQL. There's a table lah. So essentially, when there's a table, right, and there are columns, then that is structured data lah. But you know, when we speak with people, we go back and forth and we talk to people. We have conversations. There's no columns lah. There's no way to really structure the data. I mean, I'm speaking loosely lah. That's why it's called unstructured data lah. So NLP pipeline is a systematic sequence designed to transform raw, unstructured human language into a format that machines can interpret or analyze lah. So in its raw form, that's why you do embeddings, you do engrams, because the sentence on its own, you need to nudge the computer or you need to use certain techniques to convert it into numbers, right? So that you can put into a AI model, and then the AI model will be able to do some prediction. Okay, so there's text acquisition, there's cleaning, there's pre-processing, such as tokenization, where sentences are broken down into individual words, or this word should have haunted you quite a bit over the past few weeks, which is tokens, right? Because tokens doesn't have to be words. It can be like half of the word. The single character is also a token. So these are tokens. And then to further normalize these other definitions, you roughly saw from the video lah. Okay, so once the text is refined, it undergoes feature extraction, converting words into numerical representations like something or vectors. Okay, like word embeddings or vectors lah. So when you think about word embeddings, if you cannot remember what was talked about for word embeddings, is like this map that can be two-dimensional, three-dimensional, or many dimensions. Every word has a position. So it's a XY coordinate, it's XYZ coordinate on the map lah. Okay, so you can think of it as a map, and word embeddings and vectors lie on the map lah. Okay, so finally, these structure inputs are fed into modeling algorithms lah. Okay, so there are a lot of algorithms. Later we will go through the main algorithm. When I say modeling algorithm, it technically means AI model lah. And when I mean AI model, for most ChatGPT use cases will be the topic of neural networks that we'll be talking about lah. So I reiterate one more time is that usually neural networks are being taught in like either a 6 week or 12 week course. So we can't really cover all the details for today, but at least you have some taster for today. Okay, but before we go to the algorithm, just some refresher for n-grams and embeddings lah. Okay, so embeddings, the word embeddings is to represent words as a dense vector. N-grams, just now I show you the bigrams. You can pick pairs of words or try pairs, I don't know, like combinations of words lah. Don't know what three would be called, like triplets of words. Yeah. As mentioned, these two are tools lah. So embeddings and n-grams are tools. So theoretically, you can combine them and use them, or you can use them separate lah. Okay. The point is to understand that these are all tools actually, and when you're experimenting on a model, when you have your own data set, you want to train a model, just recall that there are a lot of tools that exist. The tools that you know will be embeddings and n-grams. There are a lot of other tools, but just know that there are tools, and then your job, if you are going to do this kind of data analytics, is to explore different tools and experiment and see if they do well lah. Okay, so do well, that part will be explained 2 weeks, 4 weeks from now. For 3 weeks from now, which how do you know whether a model is doing well lah? Okay, so why is it better? So if you just look at n-grams, okay, let me so just look at the sentence. I'm delighted to be here. He was happy to be here. Let's look at an example of n-grams. So we look at n-grams is I, and then there's a he. I'm just looking at the bullet points now. Okay, so but if you look at n-grams and just predict using n-grams, right? So it's like the next word prediction. If predicting in pairs or three or triples of words or four words together, you can sort of predict the next word lah. So I am, you predict word by word, delighted to be here. Okay. But if I look at it in a different way, when we do it in more of like a word embedding space, so you can see at the bottom, the I, he, was, am, right? So these have a certain space. These have certain coordinates in a space. So when these are joined to each other, that's where the direction of the flow of the model will decide lah. So the prediction of the next word is based on the distance. For example, from I to M, right, is the distance lah. So you're looking at the distance to predict the word lah. Okay, so I am delighted is a distance as well, and then delighted to be here, it's also distances, and that's when you convert these to numbers, you can train your machine learning model or AI model, because all these models only work with numbers. They don't really work with just words on its own lah. Can that be improved? Not, I mean, yes, it can be improved, but if you are going to learn how to make AI models, then you also need to learn the process lah, of how to help computers understand. And numbers is the easiest way to understand lah. Okay, but other than that, the n-grams, the idea of sequentially taking words, is about understanding its context as well lah. So imagine that the middle word, the middle square or the middle color, actually color also works. The color of this middle in the middle of all these blocks, so 5 blocks each, right? The middle color, or if you want to use word, imagine these are all words. Each square has a word. The middle color, the middle word is predicted based on the context of the words that are surrounding it, uh, or it's giving definition to the words around it lah. So this is something like the one in the left, or the last one is the next word, or the last box color is predicted by the box colors before it lah. Okay, so there's not really much way to explain whether it's better or not, but just apply it when you can. Okay. So now we will segue. If I'm not wrong, yeah, we segue towards the most important concepts that you will learn for today, and it probably be the main takeaway for, in my opinion, for your whole course. So today's seminar, I believe, is the biggest takeaway lah. If you haven't done machine learning, this is gonna fly by your head very fast. But if you've done machine learning, then the next step is actually to do deep learning lah. Okay. So the definitions on the slides, when we talk about classical machine learning as well as deep learning, traditionally there are two main definitions now. So machine learning, as the name suggests, is how the computer learns. Okay, yeah, how the computer learns. Okay, I pause for a while. I see uh, Kana Petson has a question. So embedding uh, is a technique to cluster words with similar meaning. Yes, I mean, loosely speaking, yes. Okay, but if you are not familiar with this definition, I think I went through this quite in depth for the previous seminar. So you can look at the recording, and that one will help you understand because there are a lot of visuals there as well, and there are a lot of videos and websites visuals for you to see as well. Okay, so yeah, but if you need any more clarification, you can let me know as well. But 2 weeks ago, the seminar 2 is where you get all the information for embedding. Okay, so as I stop there, so machine learning is this idea that you have to do feature engineering yourself lah. You have to choose the features yourself lah. Deep learning is this other idea whereby the neural networks will choose the features for you lah. Is that really true? I don't really like the definition technically, because most people still choose their features. But if you somewhat know what artificial neural networks are, or what neural networks are, they typically use very smart mathematics to predict patterns that we cannot lah. And I realize I don't have the other definition, or the definition that I usually explain is that a neural network functions like a neuron in somebody's head lah. So I think in the 20th century, somebody actually wanted to model the neurons in the brain into a mathematical algorithm. So I think you just search online, the paper that came out of neural networks is in the 20th century lah. But then what really happened was that it took some time to be able to exploit these mathematical algorithms that were modeled after the human brain, because there wasn't a lot of processing power lah. So because when processing power started to increase, and that's why later I'll show you some things about CPUs and GPUs, is that when processing power started to increase, that was when that these neural networks could then be exploited. Exploited means that you will sort of need a lot of power, a lot of very good computer chips, a lot of good GPUs, graphical processing units to be able to run these neural networks lah. And that is why I don't have statistics here, but when you go and search online, when you go search online and they talk about large language models, they talk about ChatGPT, they talk about Gemini, they talk about all the different generative AI tools that you use, right? Sometimes they'll tell you that it's very expensive to train these models, and that's because the fundamental of it is neural networks. So it's not as simple as saying everything inside the GPT-3 model is a neural network, but it's okay to say that the fundamental technology behind all this is the neural network that is sort of crafted based on the human brain, and explain more about that later lah. But these definitions are quite fluid lah, because I mean, as usual, in a corpus of text, meaning changes quite often, as what we have saw 2 weeks ago. Okay. Okay, so neural networks is something that is very abstract. Okay, very abstract. No, it's not. Okay, it's not too abstract, but it's very hard to show using slides, lah. So that's why there are some videos for me to show here and there, or there are some different kind of websites that are graphical for you to understand, lah. Okay, so we're going to talk about next word prediction because that's what we have been doing for all the time. But let me show you a video of what a neural network is.
Here are 5 things.
Okay, so before we start that, oh, okay. Before we start
about
this,
neural
so neural networks, if you look at this, don't know how to explain it lah. Traditionally, it's called graphs lah, but some people call it a net lah. Okay, but generally, what this is, right, is that think of it like if you have heard before in neuroscience, is that in your brain you have a lot of neurons lah. So your brain on its own, there are these dots that connect with each other, and somehow they pass electricity through each other, and just by passing of electricity, your brain functions lah. So this is the model. This is something like what it looks like. So this guy is going to try to explain a bit about it, and then I will comment on it.
Networks in under 5 minutes. Number 1, neural networks are composed of node layers. There is an input node layer, there is a hidden layer, and there is an output layer. And these neural networks reflect the behavior of the human brain, allowing computer programs to recognize patterns and solve common problems in the fields of AI and deep learning. In fact, we should be describing this as an artificial neural network, or an ANN, to distinguish it from the very unartificial neural network that's operating in our heads. Now, think of each node or artificial neuron as its own linear regression model. That's number 2. Linear regression is a mathematical model.
Okay, so the complexity is that within each circle, within each ball, within each node, okay, it's not really linear regression. It does some form of regression. I wouldn't say it's linear regression. It does some form of regression. And what regression means, that it does some form of prediction of a number. Okay.
That's used to predict future events. The weights of the connections between the nodes determines how much influence each input has on the output. So each node is composed of input data, weights, a bias or a threshold, and then an output. Now, data is passed from one layer in the neural network to the next in what is known as a feed-forward network. Number 3. To illustrate this, let's
so what this jargon is that information being passed. What that means is that imagine that you can put one word here, like you give 2 words lah. So I am, and then you want to predict the next 2 words. I am studying now. So something like that lah. So you'll give I am, and then it will pass the values through this network, and then it will spit it out at the end lah. Okay, so that would be an example. The technical term is called feed forward. But the technical definition is a bit too complicated to explain in one class. So just take note that this is just called feed forward lah.
Consider what a single node in our neural network might look like to decide, should we go surfing? The decision to go or not is our predicted outcome, or known as our y-hat. Let's assume there are 3 factors influencing our decision. The wave's good. 1 for yes or 0 for no. The waves are pumping, so x1 equals 1 for yes. Is the lineup empty? Well, unfortunately not, so that gets a 0. And then let's consider, is it shark free out there? That's x3. And yeah, no shark attacks have been reported. Now, to each decision, we assign a weight based on its importance on a scale of 0 to 5. So let's say that the waves, we're going to score that one. Yeah, no, this is important. Let's give it a 5. And for the crowds, that's W2. Not so important. We'll give that a 2. And sharks, well, we'll give that a score of a 4. Now, we can plug in these values into the formula to get the desired output. So y-hat equals 1 times 5 plus 0 times 2 plus 1 times 4, then minus 3, that's our threshold, and that gives us a value of 6. 6 is greater than 0, so the output of this node is 1. we're going surfing. And if we adjust the weights or the threshold, we can achieve different outcomes. Number 4. Well, yes, but number 4, neural networks rely on training data to learn and improve their accuracy over time. We leverage supervised learning on labeled datasets to train the algorithm. As we train the model, we'll want to evaluate its accuracy using something called a cost function. Ultimately, the goal is to minimize our cost function to ensure the correctness of fit for any given observation. And that happens as the model adjusts its weights and biases to fit the training data set through what's known as gradient descent, allowing the model to...
Okay, so I'll just stop there because there are a lot of technical things. Okay, I don't think that's a very good way of explaining, but just to let you know, there are some jargons and you'll be lost here and there, but I think it's fine. I mean, I think it's fine because we don't have that much time to go through all this in detail, lah. But just for you to know. Okay, so besides that, sorry, when I was saying, usually it's very hard to sort of explain these things without any form of visualization, lah. Okay. So let me give you a sample. Okay, I think this sample may be quite good. I'll show you this sample. Then after I'll let you play with it lah. Then you can go for a break as well, I guess. With that. Okay, so what this is that this is a TensorFlow Playground website. So TensorFlow, if I'm not wrong, is made by Google. Okay, so you can see what's happening here is that this is a neural network. This is the input, and then this is the 4 neurons. I can add more neurons that I can take out as well. But how many? I can take out so many. Okay, I can add more neurons and I can add more neurons lah. Just ignore the fact that there's a lot of math that goes into these things. Just ignore lah. But you see, when I scroll through, then you can see there are weights lah, there are things like that. But just ignore lah. Just ignore that. There's a lot of things that you don't know. But this just a simulation of the most high level aspect first lah. Oh, so I can add more layers as well. Okay, so I can add more layers. So look, looks so cool. Yeah. Yeah, so basically what I'm trying to do is that sorry, what this model is trying to do is that it's gonna train a decision boundary, or a simple word of explaining is that it's gonna train itself and it's gonna try to, with the data sets that are being given, it's gonna try to split, trying to find the split. Okay, so let me press play, and that's the process that the model is being trained. So it's finding the decision boundary per se. So how to split the orange from the blue lah. So the data set not very good lah, because it's too simple, but just for illustration. But if I change the data set to this, and then if I start training the neural networks, the neural network trying to predict where the blue should lie and where the orange should lie lah. So you can see after a process of 9 seconds of training, it is able to split that. And then if I do this and then I press play, and then it will try to find a way to split the data set into its groups. But is it able to do that? Doesn't look like. It looks like it has lost. Yeah. Yeah, it looks like it doesn't really work that well. If I increase the neurons, does it help? Okay. Okay, never mind, not the point. Okay, but let's see, should I go through yeah, maybe not. I think we can take a short break first, but at the same time, it's for you to try this website lah. Okay, so I'm gonna send you this website. You can try this out and play around with the neurons lah. So I think there's some things for you to read here as well. So uh let's you can try if you want to try. If not, you can just have a break and then we can come back at 8 p.m. lah. Come back 8 p.m. So you can try this out. This is something for you to experiment with lah. Okay, so you can experiment neural networks. You can add layers like this. You can add neurons as well. And then these are the data sets that it's trying to predict as well lah. Okay, so you can try that out. Okay, so test. Checking if the mic is working. Okay, yeah. So it's about 8 o'clock again. So the reason why I am asking you to try this link is because there are too many things to explain. So uh maybe you understand a bit by a bit may help. Okay. So things to take note is that there will be later I'll show you some code. I mean, not later. Now I'll show you some code, and then you'll see a bit of the complexity of the code lah. So there'll be layers, then there'll be neurons in each layers. There'll be a lot of numbers lah. But as I said, if you don't get much of, I mean, if you don't understand the most of this lesson, it's not because it is too hard. Okay, it's too hard, of course, but but the honest truth is that it takes like a 6 week course, 7 week course, or even a 12 week course to go through these details on the high level lah. Okay, so I'm gonna open some code to show you uh how these neural networks will look like. Oh wait, no, I already have it. Let me check. Let me grab it. Okay, so here, I think I have shared. Let me try to share it first. Then you can look at it on your own. We'll be using this notebook for the most of today. We'll be using this notebook for most of today. Uh, so if you're bored, you can just scroll through and read the code if you want to, because most of the content will be from here lah. Okay, but basically, what the artificial neural network? Let me try to zoom in. If you haven't used this before, this is Google Colab. So I sent last week's lab to all of you by use Google Colab because Kaggle has this policy whereby if the notebook is too big, I cannot upload it there. So do not waste any time. I'll just use Google Colab from now on. Next week, I'm pretty sure almost all of you have tried Google Colab, but if you have not, then next week I'll show you how you can run your own data sets in Google Colab, as well as use the GPUs as well. Okay, but Google Colab is good because it is directly linked to your Google Drive lah. Okay, so for example, if you want to do artificial neural network next word prediction, what should we do? Okay, so some of the definitions that you have seen before is that if I have my vocabulary, hello, how are you, greetings, let's define this as the database. Let's create some form of word to index. So for each word in the vocab, right? So for each word in this vocab, I want to create a word key and then index. Uh, index value. So that's what I'll do. So that will be the data set, and you saw this a lot in last week's lab lah. Okay, so what you can do is that okay, let's skip all this part and let's just look at the sentences lah. So hello world, how are you? Hello, greetings. Okay, so in a machine learning slash artificial neural network, you need to give it its inputs and its output lah. So okay, now I regret closing this. Let me open it again. You need to give it its input and output lah. So we're gonna give it certain inputs and we're going to ask it to train and then predict its certain outputs lah. So in this case, the inputs are x1, x2. I mean, you can have x squared, you can have as much as you want. These are the inputs. This is the output of the neural network lah. In neural network's case, but for machine learning, it can be either way lah. Okay, so okay, so this is a lot of data pre-processing. So I'll just skip this first. So it's just to do the processing. But let me show you how to define a tree neuron artificial neural network. So there'll be input layer, which is the size of the vocabulary. There'll be a hidden layer, which is 3 neurons, and then there is an output layer as the size of predicting the next word lah. Okay. So what is happening here is that you can see that we're gonna define the hidden layer to be 3. Then there's some math that is W1, B1. There's just a lot of math that is here, and then we're gonna ignore a lot of the math down here. But just to let you know that if we are only going to define one hidden layer, or one input and output hidden layer, if you just do a neural network, then there's a formula to do the hidden layer lah. But it's not so complicated usually. So sometimes you just use the library as well lah. But so you can look at it, but this is the raw form of the formula lah. There'll be some form of dot product that will predict the next word, and then it will just give to the output, and you do some for prediction as well lah. Okay, so basically what is happening is that you're not meant to understand the code, but just showing you certain ways of writing it. Is that when you're doing probabilities, you're predicting the next word, you are giving it the embedding matrix, you're giving it certain mathematical values lah. Then it will do some form of prediction that way lah, so you can see it. Okay, so this one is more of the hidden math behind this. So you just need to look at is the predict next word probabilities. So this part here is the way of predicting and the way of writing a single layer of neurons lah. So a single layer, what it will look like is if there's only one layer, and then in the case of here, there is only there's only one layer lah. So one layer with three neurons, then this is three neurons. Three neurons will be somewhere here lah. Yeah, so there's some math that's involved in it, but I will help you extract the math so that you don't really have to know what is going on lah. But this is just for additional reference to see lah. Okay, so not, as I said, not here to explain the code, but just for you to see and to understand lah. Okay, so there'll be some math involved, but you don't need to know the math so well, just need to know there are some libraries that you can use lah. Okay, so the next step up from neural network is the recurrent neural network lah. So what is happening is that think of these blocks of A as there's neurons inside lah. We don't know how many, but there can be a bunch of neurons that's inside. And inside the bunch of neurons, there will be a prediction that goes out, and then you'll pass the information to the next neuron, pass the information next neuron. Hard to explain. Let me show you a video to help you visualize and understand it.
Hi, and welcome to an illustrated guide to recurrent neural networks. I'm Michael, also known as LearnVector. I'm a machine learning engineer in the natural language processing and voice assistant space. If you are just getting started in machine learning and want to get some intuition behind recurrent neural networks, this video is for you. If you want to get into machine learning, recurrent neural networks are a powerful technique that is important to understand. If you use smartphones or frequently surf the internet, odds are you use applications that leverages RNNs. Recurrent neural networks are used in speech recognition, language translation, stock prediction. It's even used in image recognition to describe the content in pictures. So I know there are many guides on recurrent neural networks, but I want to share illustrations along with an explanation of how I came to understand it. In this video, I'm going to avoid all the math and focus on the intuition behind RNNs instead. By the end of this video, you should have a good understanding of RNNs and hopefully have that light bulb moment. So RNNs are neural networks that are good at modeling sequence data. To understand what that means, let's do a thought experiment. Say you take a still snapshot of a ball moving in time. Let's also say you want to predict the direction that the ball was moving. So with only the information that you see on the screen, how would you do this? Well, you can go ahead and take a guess, but any answer you come up with would be that, a random guess. Without knowledge of where the ball has been, you wouldn't have enough data to predict where it's going. If you record many snapshots of the ball's position in succession, you will have enough information to make a better prediction. So this is a sequence, a particular order in which one thing follows.
So what he's saying is that imagine you have 1, 2, 3, 4, 5 balls. You know that each ball is the time before it. So at now, 1 second before, 1 second, 2 seconds before, 3 seconds before, 4 seconds before, we have this sequence of the balls. The balls are in this sequence. We're able to predict the next sequence, which is where the ball will be in the next second, if the current second is here lah. So if you mirror it with words function in the similar manner. There's order to words as well.
Another. With this information, you can now see that the ball is moving to the right. Sequence data comes in many forms. Audio is a natural sequence. You can chop up an audio spectrogram into chunks and feed that into RNNs. Text is another form of sequences. You can break text up into a sequence of characters or sequence of words. Okay, so RNNs are good at processing sequence data for predictions, but how? Well, they do that by having a concept I like to call sequential memory. To get a good intuition behind what sequential memory means, I'd like to invite you to say the alphabet in your head. Go on, give it a try. That was pretty easy, right? If you were taught the specific sequence, it should come easily to you. Now try saying the alphabet backward. I bet that was much harder. Unless you practiced the sequence before, you'll likely have a hard time. Here's a fun one. Start at the letter F. At first, you'll struggle with the first few letters, but then after your brain picks up the pattern, the rest will come naturally. So there's a very logical reason why this can be difficult. You learn the alphabet as a sequence. Sequential memory is a mechanism that makes it easier for your brain to recognize sequence patterns. Alright, so RNNs have this abstract concept of sequential memory, but how the heck does it replicate that concept? Well, let's look at a traditional neural network, also known as a feed-forward neural network. It has an input layer, hidden layer, and output layer. How do we get a feed-forward neural network to be able to use previous information to affect later ones? What if we add a loop in the neural network that can pass previous information forward? And that's essentially what a recurrent neural network does. An RNN has a looping mechanism that acts as a highway to allow information to flow from one step to the next. This information is the hidden state, which is a representation of previous inputs. Let's run through an RNN use case to have a better understanding of how this works. Let's say we want to build a chatbot. They're pretty popular nowadays. Let's say the chatbot can classify intentions from the user's inputted text. To tackle this problem, first we're going to encode the sequence of text using an RNN. Then we're going to feed the RNN output into a feed-forward neural network, which will classify the intents. Okay, so a user types in, "What time is it?" To start, we break up the sentence into individual words. RNNs work sequentially, so we feed it one word at a time. The first step is to feed "what" into the RNN. The RNN encodes "what" and produces an output. For the next step, we feed the word "time" in a hidden state from the previous step. Remember that the hidden state represents information from all previous steps. The RNN now has information on both the word "what" and "time." We repeat this process until the final step. You can see by the final step, the RNN has encoded information from all the words in.
Test. Okay, so just a short reminder is that he's giving a good example, which is if you are going to do a prediction through on the top row is O1, O2, O3, O4, O5. You're gonna do some form of prediction. If you want to do some form of prediction lah. But you can always say that the O5 you want to take only O5 because O5 is the next word prediction lah. So when you give the question what time is it, you're hoping that O5 is going to tell you 8:10 p.m. lah. Okay, but what to take note about this is that every single ball is not a neuron. Every single ball is not a neuron. It could be, but every single ball, as how he explained it, is a neural network lah. So there's a bunch of neural networks. When we go back to just now, that idea is that there can be a lot of those neurons, and they do some form of mathematical thing. They take in the what, and then they do some form of mathematical thing. But the output you want to pass to the next neural network with that interacts with time lah. So this time here, there will be the input for this neural network is time, but there's also a second input which is from the previous neural network, and then the is the third neural network. It takes in the data, but it takes the information from before the neural network. So actually, what he was also trying to illustrate is that you see the colors of the balls. This is like a blue, this is like a green, this is like a yellow, orange, and then this like a red, right? But what you can see if you look at the last ball, right? If you correspond to the colors of each of the balls, so you can see the blue color is very smaller. So this is intuition whereby when you're passing information, the what, right, has the smallest percentage of sort of like importance when it comes to the last word that is being put in, or the last token that is put in, which is the question mark lah. So this recurrent neural network is taking is sort of using the information from previous steps, on this case from previous words lah, because what is represented by this color, time is represented by this green, yellow is the is, and then orange is the it, and then this red color is the question mark lah. And then application for this is what time is it, and then you're hoping that O5 is, if it predicts the next word, is to tell you what time it is lah. So recurrent neural networks, we did the byte pair encoding, right? Or we did the word to VEC, right? So those are models, but this neural network is a different model to do different way of prediction.
In previous steps. Since the final output was created from the rest of the sequence, we should be able to take the final output and pass it to the feed-forward layer to classify an intent. For those of you who likes looking at code, here are some Python showcasing the control flow. First, you initialize your network layers and the initial hidden state. The shape and dimensions of the hidden state will be dependent on the shape and dimension of your recurrent neural.
The feed-forward neural network is not that important, but just treat it as it's another neural network that does the prediction for you, lah. Then the hidden state is because there are four
First, the feed-forward layer encoded information.
There are sort of like four balls or yeah, can be any number of states lah, but generally there is four lah. Four here lah. Also can lah, yeah.
Information from all the words casing the control flow network should now contain information from all your previous steps. You continue to loop until you're out of words. Last, you pass the output to the feed-forward layer and it returns a prediction. And that's it. The control flow of doing a forward pass of a recurrent neural network is a for loop. Okay, now back to our visualization. You may have noticed the odd distribution of colors in the hidden states. This is to illustrate an issue with RNNs known as short-term memory. Short-term memory is caused by the infamous vanishing gradient problem, which is also prevalent in other neural network architectures. So as the RNN processes more steps, it has troubles retaining information from previous steps. As you can see, the information from the word what and time is almost non-existent at the final step. Short-term memory and the vanishing gradient is due to the nature of backpropagation, an algorithm used to train and optimize neural networks. To understand why this is, let's take a look at the effects of backpropagation on a deep feed-forward neural network. Training a neural network has three major steps. First, it does a forward pass and makes a prediction. Second, it compares the prediction to the ground truth using a loss function.
Sorry, I paused it, but what it's saying is still very abstract. What it means is that imagine if you are putting in the words I want to, and then I want to, and then you're hoping that the next word prediction is all the way on the top lah. So I want to, and then it will do some math. You'll go through this. So what he's saying is that there's the feed forward step, which is then the model should go up.
Steps. First, it does a forward pass and makes a prediction.
Yeah, so so for example, I want to, and then the prediction could be sleep. I want to sleep, and the prediction may be sleep lah. Based on the probabilities lah. Same thing. Algorithm only does its probabilities.
Second, it compares the prediction.
Okay, so this is this supervised learning, which is the loss or the error rate or the difference is whether the model is performing well lah. Which is, for example, if I'm training it, right? Training a model, I will give it I want to, and then I already know that the next word is sleep. But then so I'll train the model to see can it predict what I want, which is I want to, and then hopefully at the end it will say sleep lah. But if it doesn't say sleep, it's like I want to, then you put inside, then it feed forwards and go the way up, then it says eat. So then what is the difference lah? The difference will then be I said I hope it told me sleep, which is the true value, and then it predicted eat lah. So you can convert eat and sleep into numbers, and then that is the difference, and that's the error rate lah. So it's telling you that you gave me the wrong word, but how much is it different? You can use a word embedding to give it the number like eat and sleep, and then you can minus it. Like, so for example, if I want to eat is in the predicted, right? Imagine predicted is the word eat is 0, and then the truth, which is sleep is maybe 1. The value is 1. So the loss or the difference will be 0 minus 1, -1. Yeah. And then with that -1, it's like you're giving feedback to tell the model this is wrong, and then it will try to correct itself lah. That's why neural networks have this thing whereby it tries to correct itself.
To the ground truth using a loss function. The loss function outputs an error value, which is an estimate of how badly the network is performing. Last, it uses that error value to do backpropagation, which calculates the gradients for each.
Yeah, so the backpropagation is the very mathematical method that says that if the error rate is very big here, which as I said, I want to sleep, and eat. I said the difference was eat is like 0, sleep is like 1. So 0 minus 1, the difference is 1. But what if actually the truth is that I want to what other words? I can't think of any word now. But what if the value I want to run? The truth is run is actually 200. So the loss would be eat is 0 minus 200, then the error is negative 200, and then it will make a change lah. So it will do some changes on its own lah. There's some mathematics that will do the changes for it lah.
Each node in the network. The gradient is a value used to adjust.
Okay, then maybe I won't go through this in detail, but I'll just put in the chat in case you want to save the link and you want to watch it on your own, because I mean I've been using this video to explain RNNs for a long time, and I felt that this is a good video lah. Okay, so RNNs has its certain way of running things lah, and that logic lah. So there are other links for you to look at RNNs, but let's go through I think the next aspect lah, which is you remember when we talk about embeddings, but at the same time we talk about the idea of contextualized embeddings lah. So what is contextualized embeddings? These are very big words, but these are your large language models, and they use contextualized embeddings lah. Let me just jog your memory. Which is, if you look at n-grams, it gives the context of the bigram, which is the quick brown fox, and then the trigrams, the quick brown fox. It will just take bigrams will take 2 words, trigram will take 3 words. There's no meaning, it just takes the frequency of words lah, right? But then if you static word embeddings, you will have sort of a vector that's associated with each word lah. So apple, if you do a word embedding on it, it could translate to, in this case here, it translates to 0.2, 1.7, 0.3, etc. lah. It translates to a certain number lah. But the thing with these static word embeddings is that you have these, if you use the same word apple, apple, the food that you eat, will have the same vector, have the same number as Apple, that is the iPhone lah. So this does not give it context lah. But what about the last part, which is contextualized embeddings lah, which is if you ate an apple, should give it the vector which is with context lah. And then if you give it apple the product, it should have a different word vector lah. So contextualized word embeddings, in some sense, it saves the same word as different vectors lah. Okay, so that is that concept. And for contextualized word embeddings, they are used in the large language models lah. So for you to take note, okay? Okay, so let's see if you're able to understand or remember the definition of contextualized embeddings, because this is quite necessary. Because when we move on, large language models, you just need to know that the breakthrough in large language models is contextualized embeddings. So contextualized embeddings helps to view them in the final stage of how machines read text. Okay, the evolutions of how machines read text lah. So this is still the most state of the art lah. Use some form of contextualized embedding methods. Moving from simple counting to deep understanding. Initially, NLP relies on first thing that we learn, n-grams, which are contiguous or side by side adjacent. That's what contiguous means. Sequences of n items like words or letters that help predict the next word based on local frequency. So how many times so if I say I am, if you scan I am in a lot of reports, I am is a common word, right? A lot of documents, I am is a common word. So I am is high frequency lah, but fails to grasp the actual meaning. So this involves into static word embeddings, like word2vec, which assigns each word a fixed numerical vector in high dimensional space so that king and queen can be mathematically related. Or in another sense, king can be 0, queen can be 1. And with that, you can do some form of arithmetic, right? So the example of the analogous word embedding was that king minus man plus royalty equals to queen, something like that, right? Because you can make words into numbers. Okay, so however, these models struggle with words that have multiple meanings, polysemy, because they provide the same vector for bank regardless of whether it is money, which is a financial bank, or river, which is on the side of the river bank. Okay, so contextualized embeddings represent the modern standard by using deep learning to generate dynamic vectors that change based on the surrounding text. So that's just to highlight the fact that when we did all the previous technology for the first two seminars, I wouldn't say throw it out the window lah. I wouldn't say throw out the engrams, throw out the word embeddings. I wouldn't say throw them out the window. But what I'm saying is that for these models, they use neural networks. So they use the balls or the structures to determine the values of words lah, and how they can relate to each other better than word embeddings lah. Not that you throw them away lah. Just remember that deep learning is still the state of the art lah. So that's why all your generative AI models, all your ChatGPT, Gemini, they're all using neural networks fundamentally because they can provide contextualized embeddings lah. Okay, so one way to visualize it now is to actually look at how this contextualized embedding model works lah. So if you see the output on the top, basically you're creating a map of where certain words belong to in the sentence lah. So I would like a foot. The ball is 1 foot away. My left foot hurts from he's leaning on his right foot. So when each word goes into the embedding layer, it trains in the model, your output, then it will create its own output that's similar to the word to vec lah. So foot, maybe these 2 foot, my left foot, my right foot, has slightly different contextual meaning because we have 2 feet, but the left foot is the one on the left and the right foot is the one on the right. So that can be here, they can be quite similar. I would like a foot long subway, a foot long sandwich, right? The ball is just 1 foot long away. They're both distances, but you can see that some distance is the measurement of foot, some distance is the measurement of proximity or distance lah. Okay, so the neural network is the model layers lah. So when you see layers, then by all means it should be neural network layers to begin with lah. Okay, so just to remind you, one way to do this contextual embeddings is that your input can be you mask out the word, meaning that there is a word here actually. We mask protect, like mask protect our environment. Okay, so this mask is you are giving it context, but then you are just blocking out this word, and you are hoping that within this context, the deep neural network layers will be able to do their prediction lah. So a masking would be an example of how to do it. There are many ways, but this is just one example to do it lah. Okay, so for example, we should, so for example, we should, and then you can mask the other words lah. This could be the next word prediction as well lah. So for example, we, and then there's no context, so it can be we should, or then it can be we should, and then predict the next word. This other way of doing it also can lah, if you want to do next word prediction lah. Okay, but right now, the other key thing and the one that we'll be doing in our lab will be this thing called the LSTM, the long short-term memory neural network. So let me show you a sample of what it is. Okay, let me show you a sample of what it is. Just to reiterate lah, just because this guy explains it very well and it's very visual lah, so it will help you learn for sure lah.
Hi, and welcome to an illustrated guide to LSTMs and GRUs. I'm LearnVector, and I'm a machine learning engineer in the AI voice assistant space. In this video, we'll start with the intuition behind LSTMs and GRUs. Then, I'll explain the internal mechanisms that allow the LSTMs and GRUs to perform so well. I'll follow up with an example. If you want to understand what's happening under the hood for these two networks, then this video is for you. LSTMs and GRUs are the more evolved versions of the vanilla recurrent neural networks. During backpropagation, recurrent neural networks suffer from the vanishing gradient problem. The gradient is the value used to update a neural network's weight. The vanishing gradient problem is when the gradient shrinks as it backpropagates through time. If a gradient value becomes extremely small, it doesn't contribute to much learning. So in recurrent neural networks, layers that get a small gradient update doesn't learn. Those are usually the earlier layers. So because these layers don't learn, RNNs can forget what is seen in longer sequences, thus having short-term memory. If you want to know more about the mechanics of recurrent neural networks in general, you can watch my previous video, An Illustrated Guide to Recurrent Neural Networks. LSTMs and GRUs were created as the solution to short-term memory. They have internal mechanisms called gates that can regulate the flow of information. These gates can learn which data in a sequence is important to keep or throw away. By doing that, it learns to use relevant information to make predictions. Almost all state-of-the-art results based on recurrent neural networks are achieved with these two networks. You can find LSTMs and GRUs in speech recognition models.
Okay, so long story short is that if you, okay, so classically when deep learning is being taught lah, you will see LSTM and then you see GRU, and it's very confusing because there are a lot of things inside. All I can offer you is just, you don't really need to know it, just treat it like it's a black box, but just know that on a high level that there's some mechanics lah that try to help with the long short-term memory issue. So just now we encountered that RNNs have a problem with long-term memory. So these gates are here to help that. You don't need to know the function of each gate per se, but just be aware of it.
With these two networks. You can find LSTMs and GRUs in speech recognition models, speech synthesis, text generation. You can even use them to generate captions for videos. Okay, so by the end of this video, you should have a solid understanding of why LSTMs and GRUs are good at processing long sequences. I am going to approach this with an intuitive explanation and illustrations and avoid as much math as possible. Let's start with a thought experiment. Let's say you're reading reviews online to determine if you want to buy a product. When you read the review, your brain subconsciously only remembers important keywords. If your goal is trying to judge if a certain review is good or bad, you pick up words like amazing and will definitely buy again. You don't care much for words like this, gave, all, should, etc. If a friend asked you the next day what the review said, you wouldn't remember it word by word. You might remember the main points though, like it was a perfectly balanced breakfast. The other words would just fade away from memory, unless of course you're one of those people with perfect memory. That is essentially what an LSTM and a GRU does. It can learn to keep only relevant information to make predictions. In this case, the words you remember made you judge that was a good review. To understand how LSTMs or GRUs achieve this, let's review the recurrent neural network. An RNN works like this. First, words get transformed to machine-readable vectors. Then, the RNN processes the sequence of vectors one by one. While processing, it passes the previous hidden state to the next step of the sequence. The hidden state acts as the neural network's memory. It holds information on previous data that the network has seen before. Let's zoom into the cell of an RNN to see how the hidden state is calculated. First, the input in the previous hidden state is combined to form a vector. That vector now has information on the current input and the previous inputs. The vector goes through the TAN activation, and the output is the new hidden state, or the memory of the network. The TAN activation is used to help regulate the values flowing through the network. The TAN function squishes values to always be between -1 and 1. When vectors are flowing through a neural network, it undergoes many transformations due to various math operations. So imagine a value that continues to be multiplied by, let's say, 3. You can see how some values can explode and become astronomical, causing other values to seem insignificant. Let's see what a TAN does. A TAN function ensures that the values stay between -1 and 1, thus regulating the neural network's output. So that's an RNN. It has very few operations internally, but works pretty well. RNN uses a lot less computational resources than its evolved variants. Let's take a look at LSTMs. An LSTM has the same control flow as a recurrent neural network. It processes data sequentially, passing on information as it propagates forward. The difference are the operations within the LSTM cells. These operations are used to allow the LSTM to forget or keep information. Now looking at these operations can get a little overwhelming, so we'll go over this one by one. I want to thank Chris Olah, sorry if I butchered that name. He has an excellent blog post on LSTMs. The following information is inspired by his exceptionally written blog post. I'll include the links in the description. The core concepts of LSTMs are the cell states and its various gates. The cell state acts as a transport highway that transfers relative information all the way down to the sequence chain. You can think of it as a memory of the network. Because the cell state can carry information throughout the sequence processing.
Okay, so I think he's going into too much detail lah. But I think the idea is that can just treat it like a black box. Just understand that RNNs, neural networks, LSTMs, these are tools to help with the recurrent the memory problems lah. Okay. Okay, let me see, is there any other things I wanna share? Okay, then I think I will skip this video now lah. Okay, but then let me show you some code lah. So I have sent let me send this notebook again so you can see the notebook, and then you can scroll down to check out the notebook lah. Okay, so now you may not need to code not everything will be coded out from scratch, but there are libraries to help you with this lah. Okay, so in a certain sense, if you want to code out your own RNN, then RNN, then there's a lot of the math which is here. Predict the next word's probability lah. So you can see predict the next word probability. You need some of the values. You need the dot product lah. There's some 10. Just now you heard some 10, right? You need to do some dot product with the embeddings, with the values and the numbers that you want to train it on. And you need to do some math lah. So there's some aspects here. So I'm not going to go through the math lah, but you just need to know that RNN is like this. But this is just for the concept. But actually for the libraries, you can just import RNN lah. You don't need to write all these things lah. You import RNN, just set what to put inside, and then it should be fine lah. Okay. So RNN, there's some prediction, and then there's also LSTMs here. Okay. So yeah. So let me check what else there is. Okay. Yeah. So LSTMs will have slightly different logic lah. They were saying that inside there's a lot more values lah. So there are a lot more gates lah. There are a lot more values that it can use lah. So you can see the forget gate, there's some math to it. There's input gate, there's some math to it. There's different cell states and different output gates. So there are a lot of math to it lah. So if you see there's a lot of this. Honestly, don't need to remember, don't need to memorize all these. They don't help you per se. These are just mathematical algorithms lah. So if you can refer to it when you are if you are truly going to do RNN, LSTM, then just refer to it. Don't really need to know lah. But these are just samples of what it will look like in code. But this is with the math, but there are libraries that you don't have to do all this. You just need to call LSTM or RNN lah. Okay. Maybe I can show you a sample like RNN Kaggle. Uh, okay, so let's let it load a bit. Let's see if this person has developed RNN that is using the library instead. Okay, so I just click on RNN. Oh wow, okay, this looks like a good tutorial as well. Create RNN model. So for them, there's this thing called Keras, which is built on TensorFlow. For our lab, we'll be using PyTorch, I believe. So one thing to take note is that if you are gonna be analytics or AI engineer, then you need to say that in your resume you need to write Keras and TensorFlow is your skill set lah in developing neural networks lah. So sometimes creating RNN is just simply define RNN lah, something like that lah. Don't need to do so much of the math, just simple RNN, just write this, and this is the layers lah. So inside the simple RNN, there is 50 neurons on the inside. You can ignore the rest, and you see the 10 activation. And then at the same time for LSTM, I know he also got LSTM, but let me scroll up and use his contents page instead. So it's LSTM. Let's see. Here, okay, create LSTM. So create LSTM, it was imported here, Keras, import LSTM, then after that you just LSTM lah. Yeah. So this can be done instead of a lot of the math that has been abstracted here lah. Okay, so if you want, you can just search. Okay, maybe I'll send this in the chat. Then you can see various ways of doing it lah. But most people just like do this lah. They import LSTM lah. But if you need to do it for assignment or if you need to make your own model, then this would be example that I have sent to you, and you can try it on your own. Okay. So not so important, just know that it's a tool to help you with lah. It's a tool to help you with. And then in your slides, you also have more readings as well lah. So these are optional for you to read, for you to try if you want to try it. Okay, for you to read and for you to try if you want to try it lah. Okay, so let's go next. So of course, when you want to do language modeling, you want to do next word prediction, you can do that lah. So in terms of the idea of knowledge, when you want to predict, SUSS is located at. It's not it's not really logical. You need to memorize. That's why it's knowledge. I put the book down on the sometimes it's common sense on the table. The woman walk across the street checking the traffic over. So it's usually over maybe her shoulder because it's based on referencing. And then I was thinking about the sequence 1, 2, 3, 1, 1, 2, 3, 5, 8, 13, 12. This is the Fibonacci sequence, right? 1 plus 1 is 2, 1 plus 2 is 3. So basic arithmetic lah. So that's why next search prediction is tend to be something that most people want, and it also works well for the ChatGPT large language models as well lah. Okay, but then when we peel back, as I iterated many times, is that when you want to train a model, then the key thing is you have good data, you have a good algorithm, and then you have the compute resources to train it and to show it lah. Okay, so right now okay, let me just skip. Let me skip this. Okay, I'll skip this also because for the last two seminars, we'll be going through these details. But let's just go through the concept of training models and why training models is a bit more, okay, not really expensive, but the models require this thing called the GPU lah. So I'll give you the one-liner, which is GPUs are the best, not only for playing games, but for training models. Sorry, GPUs are also very good for mining cryptocurrency like Bitcoin. So a lot of people bought GPUs to mine cryptocurrency, and that's why GPUs are so expensive. But right now, why NVIDIA is doing so well is because the GPUs are the things that require trained models lah. So at the start, I was saying that neural networks fundamentally work very well, but require a lot of computing power, and GPUs are the computing power to help it. Okay, so but besides that, to help you with your assignments in the future, if you have not tried before, if you connect using the Colab notebook, and then you can just use their GPUs as well lah. So there are GPUs here as well. I'll go through when necessary. Okay. Gina has a question. For TMA, do we need to cite Kaggle sources if we refer to them when writing your answer? Best to put in some form of just show some form of where you get your references from lah. If not, most of your lecturers will just think that you use AI lah. Most of your profs will think you use AI. So you can cite them if you want to cite, but I recommend you just add it in somewhere lah, so that it shows your evidence of work. But with Gen AI, okay, besides the point, the problem with Gen AI is that you can easily get code with Gen AI, and code is not necessarily copyrightable lah. But for your sake, of course, because your TMA and your ECA, you need to show proof of your own work lah. So citing will be good. Just make sure that you know what you're doing lah, will be fine. But of course, citing would be one way to express that lah. Okay, so let's see the GPU versus CPU. See if it helps. Oh, video unavailable. Okay, I guess somehow this video disappeared. Okay, let's look at this video then.
In this video, we're going to compare the differences between CPUs and GPUs. Let's jump in. A CPU, Central Processing Unit, is the primary component of a computer that handles all types of computation
computation tasks required for the operating system and applications to run, and it tries to do so with minimal latency, and it's often referred to as the brains of the computer. Some of the main internal components of a CPU include the arithmetic and logic units, the ALU, which is responsible for carrying out arithmetic and logic operations. This includes basic calculations like addition, subtraction, multiplication, and division, as well as logical operations. The ALU is critical for the execution of most processing tasks within the CPU. The control unit orchestrates the operations of the CPU by directing the flow of data between the CPU and the other components of the computer. The cache is a small-sized type of volatile computer memory that provides high-speed data storage and access to the CPU. It is used to temporarily store frequently accessed data instructions from the main memory, which could be, RAM, like random access memory. And then we also have the memory, which is not part of the CPU, but is used to store data in the instructions that the CPU needs to access frequently while performing tasks. We also have multi-core CPUs, so many modern CPUs have many cores, and you may have heard of something like a 16 cores.
Okay, it's a lot of jargon, but most of what we know is still a black box for most of you. I mean, of course, in my bachelor's degree, I've studied a lot of this, but just take note lah, that the key thing between the normal CPU and the multi-core CPU is like you can think of it as like in a CPU, if this is a single core CPU lah. This CPU is like think of yourself as like the manager of one person lah. You say okay go okay for lack of a better way of saying it, go buy for me this thing that I need to use. Go and buy. Okay. Then after that
in the
for
instruction. So
multi-core
many
CPU it's like now instead of having one very good worker, you have four like slightly subpar workers. Okay, that may not be the best example, but you have like four people, and these four people now that is equivalent of the capacity of that one guy. You can split this four people to do four different things lah. So from here, you can say, the first person, I want you to go and buy this. Second person, I want you to go and research on that. Third person, I want you to take some papers, start writing down the plan. So a multi-core CPU is like you can, in this case, you can do four things at the four different times lah. Okay, but let's see what a GPU is on a very specific level.
Graphics and animation resulted in the first compute-intensive workloads that CPUs were simply not designed to handle. For example, video game animations required applications to process data to display thousands of pixels, each with their own individual color, light intensity, and movement. And that's where GPU, graphics processing units, as the name suggests, was originally invented to help render images on display devices. Mechanically, a GPU is similar to a CPU in that it is made up of many of the same components, such as the ALU, the control unit, and the cache. A GPU can handle very high throughput, and this is due to the enormous amount of ALUs. In addition, GPUs...
So I'll just summarize it on a more simpler perspective lah, is that you sort of see like the CPU is quite powerful. It can do very fast calculations at once lah, or it can do something very quickly. But then if we split this level, for example, this has the power of one. Power of one. Like the power is like one, right? So it can do things maybe like at one time speed. But then we split that one into four different cores. Then each can do a quarter of one, but yet it can do many different things at once lah. But then somebody decided that if we split that one into a lot of different processors, or a lot of different you divide it equally among a lot of these own units, right? Then all these can run their separate things or separate tasks lah. So another way of viewing it is that the example of running games or running images lah, is that you can see what this looks like. Is that it looks like the amount of pixels on the screen lah. So you don't know what is a pixel. Your computer has pixels. You may not be able to see it, but if you go close enough to your phone or your computer, you will see pixels lah. So a GPU helps render each pixel faster. But in a sense, it can do many calculations at once as well lah. So that's the difference of the GPUs, and that's why GPUs can do many calculations at one time. But a CPU can do very fast calculations, but not multiple calculations at the same time lah. But the long story short is that if you know about vectors as well as matrix multiplications, then using GPUs will speed it up lah. Okay, so that's just for you to take note, but it's also for you to take note that whenever you're running models, you should be using GPUs lah. So LSTMs wise, if you can use a GPU, if you use if you run other deep learning networks, then use GPUs lah. Okay, so maybe a lot of content for today, but the key thing is to take note lah that a lot of these things are a lot of these things can be covered usually in a 6 week time frame and not like a 3 hour time frame now. Okay. The last thing that we'll go through for today will be the idea of RNN and CNN. So just now RNN is about recurrent neural network, but I'll go through this idea called the convolutional neural network. Okay. So with this, I think maybe we take a short break first. Then after that, I'll go through the last topic for today lah. I'll go through the last topic for today. So what that means is that the okay, you can come back at the 9:05. 9:05. It's about 9:05. Okay. Uh, maybe a bit too much content for today. But I think this last part may be a bit more interesting lah. With code will be a bit more interesting. Okay. So let's look to a definition of what the convolutional neural network is. Okay. Okay. So, which example should I use? Okay, I'll use this visualization over here lah. Okay, so I like to use this visualization. Let me show you what this is about. So I'm going to draw a number here, and then there's a convolutional neural network to predict what this number is lah. Okay, so maybe zero. I put zero, and then it's predicting uh the first guess. Okay, it's not turning out very well. The first guess is saying that it's 9. Second guess is saying it's 7. So it's neither 7 nor 9. That's a bad prediction. Let me try to draw a better 0. Okay. First guess is 0. Second guess is 8. Okay. So maybe I draw like a 1. May predict. Oh, so it looks like 7. I draw this. It looks like no, looks like a 2 also. Wow. Okay. Okay. So if I draw this, oh, okay. Looks like a prediction not very good. This model 1. Okay, so size also matters as well. Okay, so just to show you what this is, I'll copy and I'll send it on the chat. If you want to try, you can. Okay, so just to show you what this is that think of it as this is the input. This is the input at the bottom. Then these are the neural networks lah. So this is one layer, very long layer, ultra long layer, very long layer, very long layer, and it goes to another layer, and then it does some form of prediction. Okay, so if I click, I can see all the pixels will go to this layer and it does some form of mathematics. And then when I click here, you can see all the layers, it connects with this neuron and it does some form of mathematics. Then after it goes to the end and then it makes some form of prediction. Okay, so convolutional neural network is something like a normal neural network, but it has the convolution in it. Okay, so its use cases is a lot for predicting images lah. Okay, so let's see a video to illustrate the convolutional neural network.
To support production of more high-quality content, consider supporting us on Patreon or YouTube membership. Additionally, consider visiting our parent company Earth-1 for sustainable living and main aspects. For our discussions on convolutional neural networks, we will go with a very common example, number recognition. The reason this example was chosen is because of this great interactive resource by Adam Harley, a robotics PhD at Carnegie Mellon University. I have linked the resource in the description so that you too can experiment with it and see the internals of a convolutional network. Now, if you can recall from our example on an image pattern recognizer using a feed-forward network, we set up an idealized system and made the assumption that each hidden layer in our network would build upon further layers of abstraction, from vertical lines to combinations of vertical lines. However, in actuality, as we explained, this wouldn't happen, and the receptive fields in the network would be a lot more random to the human eye due to the architecture of feed-forward networks and how they compute. With convolutional networks, however, this isn't the case, and we could to some extent see these layers of abstraction building up. Before we delve into why and how this happens, let's first set up.
So one way to explain is that imagine that you are taking a picture and it's being used to train your face recognition system on your phone. So you can see what's happening is that if this picture is bounded by a box that I'm drawing, it's bounded by a rectangle that I'm drawing, the neural network will try to break up individual elements and take each pixel and it will start to do some form of prediction. So that is why the mid-level features now is that it's trying to break up certain pixels and use them to be able to predict where the face is.
Up the structure for the network we will be using. As with our previous example in image recognition, the input will be the individual pixels of our image, and the output the patterns we are trying to classify. In this example's case, we have 10 outputs, numbers 0 to 9. For the layers in between, we will have 2 convolutional layers, 2 pooling layers, and 2 fully connected layers. Now that was a lot of new terminology thrown around, so let's break it.
So the special thing about the convolutional neural network is usually it has this special thing called the convolution layer. I mean, technically also the pooling, but just for simplification, the convolution layer. So there's some very smart mathematics in the convolutional layer that makes it perform very well when it's predicting image-based tasks.
it down layer by layer, starting with the input. While we have already stated that the input is the individual pixels of the image, I want to mention some important details about how a computer views this image. Every image in a digital device is stored as a matrix of pixel values. This is referred to as a channel, a certain component of an image. Now with a typical digital camera, every image will have 3 channels, red, green, and blue, RGB, which you can imagine as 3 2D matrices stacked upon one another. For the sake of simplicity, we will assume our input has just one channel, the luminance of the image, with the value of each pixel represented in 8 bits. In other words, the pixel values will range from 0 to 255, with 0 indicating dark or transparent luminance, and 255 is bright. As a side note, digital systems store all types of sensor data and other information in this fashion. For example, for a convolutional network that would operate on speech, we could represent that speech as a matrix of frequency values. Coming back on topic, now that we understand the format of the input, let's finally delve into where the real magic happens, the convolutional layer. As you can assume, this layer and the network as a whole get their names from the convolutional operator, which in layman terms is the mathematical combination, in other words the dot product of 2 functions to produce a third function. In CNNs, this operation is implemented in what is referred to as a feature detector, filter, or most commonly, a kernel. You can think of a kernel as a mini matrix, orders of magnitude smaller than the input. In a convolution operation then, the kernel moves across the input image, taking the dot product of the 2 matrices and then saving the values to a new matrix, dubbed the feature map of the original image. At this point, you may be wondering how this is able to detect any features at all. Well,
Okay, so long story short, you can see the image on the left and the image on the right. The image on the left is like bigger than the image on the right. Image on the left is clearly a 0. Image on the right looks like a distorted 0, and that's because when this kernel, when it's moving, this square is moving and it's converting the image on the left to the image on the right because the space is smaller. Not the space is small because the left has lesser pixels than the right because of the size of the image, right? It's smaller already. So what's happening is that this kernel is trying to extract the minimum amount of information to ensure that the next feature that is using is significant. Or in other words, with the image on the left, am I able to remove certain information so that it still retains all the information that is needed? And after I remove them, yeah, it should look like the one on the right lah. Okay, so there are various ways to remove them, and you have to test these methods. But this method is called the convolutional layer lah, in terms of the neural network.
if a kernel is initialized with the values in a specific configuration, they can be used to transform an input image and find various patterns. Take these kernels for instance, when loaded with the appropriate values and convolved with the input image, produces an output which highlights various edges in the photo. Now I won't delve into the specifics of the various types of kernels in this video, but there are many resources that talk about them extensively, such as Computerphile and their various videos on kernels like the Sobel Edge Detector. Coming back on topic, as you can see, kernels are essentially ways to do fast computation and produce a new output. In this case, we're doing it with an image, with an effect or features highlighted. Programs like Photoshop use these simple kernels for effects like blurs, for instance. Now when we look at a typical image, take in how much is actually going on. There are various edges, shapes, textures, etc. that stack together to make various objects and the overall image we are looking at. At the start of a convolutional network, the types of kernels we'd use would be quite simple and more geometric, detecting things such as edges, corners, and simple shapes and patterns, like a circle for instance. Additionally, each convolutional layer can have multiple kernels that produce multiple feature maps of their own. So for our example, we can see that our first layer has 6 kernels, and these kernels are detecting simple patterns like horizontal lines, vertical lines, and corners on our draw numbers. As a side note, for each of the
So what that means is that he's showing the different so the input is the one at the bottom, the top one is the convolutional layer. The 7, you can see examples of 6 different 7s. So the convolutional layer will use different methods to figure out how it can reduce this 7 as the input into variations of 7 that still look like 7, but they are smaller in size generally lah. So that would be I mean that's not the most technical way to explain it, but that is generally how it is like lah. Okay, so with that let's see is there anything else I want to say. Okay, maybe we look at the last part that's looks a bit more intuitive lah.
backpropagation and gradient input pixels. In this example's case, there are 120 neurons in the first fully connected layer and 100 in the second, and as you can see, these are sufficient to correctly classify numbers with a high degree of accuracy. Now, I hope you can recall, as we've covered in videos past, during the process of backpropagation and gradient descent, the weight and bias values are tuned as the network learns. In terms of convolutional networks, those values would still be altered during this process, and also other values such as the kernel coefficients of our convolution and pooling layers. Now, before continuing, I want to stop and
Okay, maybe we stop here. I will let you, if you want to watch the video, you can. I usually like to use visualization videos. There are a lot of other ways to explain lah. Usually this whole convolutional neural networks takes 3 hours to explain for me. I mean, okay, 2 to 3 hours to explain for me. Usually, if you want to specialize in this field of AI, this would be computer vision, lah. How computer views images, lah. Okay, so that's something you can see. But let me show you more of in practice, lah, what it will look like, lah, if you want to train an image, lah. Okay, so if you have the same notebook, as always, you have the same notebook, you can follow me along. This will be a more practical thing that you can see lah. So a bit more interesting, because I understand a lot of things was already gone through today. So some people may have already tuned off, but you can start to look at this and to see what is happening lah. Okay, so for convolutional neural network, let me show you a sample of it. So we're gonna use the same digits that has been using. So I'm just gonna gloss through the code, but show you images for you to understand now. Okay, so there's this MNIST data set. If we were to split the MNIST data set to train and test, this is a sample of the MNIST data set. Similar to just now in all the videos that you have seen, this is a 5. So this is a label that is called 5. Okay, and then after that, what is happening is that similar to RNN or similar to the LSTM, right? You can define each layer yourself. So we're going to go through, these are TensorFlow libraries. Let me scroll up. Okay, so these are TensorFlow libraries. So if you want to be a real AI ML engineer or data scientist, you need to be familiar that the library TensorFlow or PyTorch lah. For PyTorch, we use the lab, but normally I teach mostly in TensorFlow lah. Okay. So for each layer, you don't have to do the math part, like the previous example of the new artificial neural networks, but you can define the layers such here. Okay, so you may not understand everything, but it's for you to take note that the input layer is 28 by 28 pixels lah, because this is actually 28 by 28 pixels. Just take my word for it lah. You can read the code if you want, but this is 28 by 28 pixels. So it's putting a 28 by 28 pixels. This is the input. Then the convolutional layer, there are 32 3 by 3 kernels. Just ignore that. I'll just abstract it. So these are some settings, and there's a pooling layer, and then it does some form of things. So sometimes if you want to read what a model is, you can do a dot summary. It'll tell you that this is a convolutional layer, this max pooling layer. So think of it as that these are layers now. Okay, so this is when I need to start running it. If not, it will start crashing on me. So I'm running it. So I run, give it some time. It's going to load the MNIST data set. I should have ran it. Okay, so it's going to load the data. It's going to process the model, and then it's going to do some settings for the model. But at the same time, it's going to start training the model to predict numbers. Okay, so I'm going to run this, and then in neural network training, you will see this thing called the epochs 1 to 5. So it's taking quite long. It's taking about 18 seconds. It'll take 18 seconds to train one epoch. So there are 5 epochs to train. So there are 5 batches that it needs to train, but it's taking too long. So this is when this is a good example that I'll change it to the GPU instead. So I will try the T4 GPU. So I click this and I click save, and then you reconnect. So I repeat one more time. I change runtime. I click T4 GPU, or you can try this TPU. I usually use this GPU because I think last time there weren't so many settings lah. So just I ran it, and then now we can see how long it takes. Okay, so the whole code has been the whole notebook has been resetted, so I have to run again. So I click run. It's going to download the data set again. It's going to download the data set. Okay, still waiting to download the data set. Okay, then it's going to do some settings for the model. This is my own model that I'm developing using neural networks, and then I'm going to start training. Okay, so just now, one epoch was going to take like 20 seconds. Now let's see how fast if I use a GPU to train it. So if I use the GPU training, wow, one epoch took like 2 seconds, 7 seconds. Yeah. So it's so much faster. So 7 plus 2, that's 9. 9 plus 2 is 11. 11 plus 2, that is 12. 11 plus 2, sorry, 13. 13 plus 1 second. So the training process was faster than just one epoch training. That's why I use the GPU lah. Okay. So that is when we'll evaluate the accuracy. So if I run the code here, that you can take a look at its own. I'll not really explain these graphs unless you're familiar with machine learning, but it's just showing how well the model has been predicting or not lah. Okay, so these are additional notebooks for you to check out at the end of today if you want to see for yourself. So I will leave it to you. I'll give you a bit more time at the end so that you can look at the notebook if you want to look at it lah. So I won't waste your time here. So in case you want to see it tomorrow when you are fresh awake, or you have the inspiration that, oh, you want to be training models like this on images, then this is the way to go lah. Okay, so you can look at this notebook lah. So I'll give you time at the end to try if you want. If not, let's move on to the next part. Okay, move on to the next part. Can okay. So the last thing you think about is like why is the topic of words, why did I show the CNN? Why did I show images lah? So let's think about what is the similarity between words and images. Let's think about the similarity between words and images lah. So if you think about it, oh sorry, if you sorry, supposed to load. Oh yeah. About okay. If you think about it, an image has certain relationship with each other lah. So the image down here, you can sort of see like there's a certain order to it, like words, right? So meaning that a face has to be above the body, right? The eyes have to be at a certain location. If the nose is above the eyes, then it may not be a person. You may not recognize it as that lah. So there's some form of sequential relationship as well lah. And that is why there's this idea of how instead of using CNNs, there's this new thing called vision transformer lah. So vision transformer is one of the latest models lah. You are using so a transformer is like ChatGPT. It is generative pre-trained transformer. Transformers now are being used to predict images as well now lah. Okay, so there are a lot of resources. Let's see a sample of the video of what is a vision transformer.
Let's understand vision transformers. We first divide the image into sub-images known as patches. This image patch is nothing but the pixel values of that area of the image. You can see pixel values of single patch. However, since this is an RGB image, instead of a single 2D array, we have 3 channels for each patch. The problem with these patches is that the pixel values range from 0 to 255. We simply normalize these values, and now the input image is ready to be fed into the vision transformer. Remember, here we are using a patch size of 8 by 8, with a total of 64 patches for clear visualization. However, in the actual vision transformer paper, their patch size is 16 times 16. To convert it into a one-dimensional array, we need to flatten all 3 normalized channels of the patch and obtain a vector. We do this for all the patches in the image and obtain a linear vector for each patch. Let's rearrange these vectors for better visualization. Instead of using these normalized pixel values directly after flattening them, we transform them into embedding vectors for each patch. This process involves taking each input and passing it through a neural network to obtain an embedding vector, 1 by 1, for each patch. Now, these embedding vectors can be treated as word embeddings. For the attention mechanism, we take the embedding vector. We make 3 copies of it to feed into the query, key, and value matrices. We get the output query, key, and value vectors for the attention layer. This is a simple process. Here each embedding vector can be processed in parallel. However, this parallelism creates a problem. I mean, how will the attention mechanism know which patch it is processing? The first patch? Or the 10th patch? Or the last patch? Just like in sentences, where the position of a word is important to understand the meaning, changing the position can alter the meaning of the sentence, even with the same words. The position of each patch is also important to understand the whole image. But how do we feed position information to the attention part of the transformer? For this, we add positional encoding to the embedding vector to incorporate position information into the vector. After adding position encoding, we get the final vector to feed into the attention block. Now the data seems ready for the attention block to develop relationships between patches. We apply multiple attention blocks and then obtain the output. After these attention layers, final output is ready. At the end, we apply a neural network with softmax for classification. One way is to take the last patch embedding and feed it to the classification network, just like we do in text for next token generation. But actually, we add an extra learnable embedding vector. The goal of this extra embedding vector is to gather all the important information from other patches using the attention mechanism for classification. Then, at the end, we feed this vector to the classification.
Okay, so I think it's a bit too complex, but then what you would then associate with is that just remove all the abstraction. Just understand that all the models that you've been doing, all the models that have been invented, somebody sat down a long time, did a lot of experimentation. They try different kinds of, they try to pick and choose different ways to put neural networks together. So for example, when I was saying we have gone through, oh, sorry, wrong. We have gone through the CNN. Okay, okay, without giving examples. We've gone through CNN, RNN, it's just variations lah. Somebody sat down, wrote a PhD paper, wrote a research paper, and then they figure out that this would be a very good combination, this would be a good solution lah. So another way, because all of you, if you are in this module for better or for worse, because you have chosen it, I will still explain to you that treat all these models like black boxes. But how do you access these models that are already done? So if you're going onwards to become somebody that analyze data, then you're gonna have to look at or the first step and the easiest step for you to do, whether it's to write on your resume or to show that you're experienced with models, is actually go to Hugging Face dot the website lah. So I think I have said this before, but Hugging Face is where you can get models lah. So for example, Vision Transformer, they'll teach you how to import the Vision Transformer, how to run it. So you can search it on, okay, I'll send it on the chat. So you can search it on your own and see how it's used lah. Okay, actually how it's used, let's see. Is there a sample of how things are used? Okay. Okay, if not, you can always click on models. Because somebody sat a very long time and developed their own model. Inside a Hugging Face, you can find a model of your own. So and for basics of pre-trained models, that's when you will start and you will use it lah. So for example, if I want based on task, okay, I realize Hugging Face website just updated its own interface. It looks like it changes quite regularly. I've been using it for a couple of years. It changes quite a lot. So for example, if I want a natural language processing model, I want to look for maybe question answering. I click on question answering. Then you can see these are a few of the latest models. I didn't know the Roberta is still quite a popular model that's being used. Okay. Maybe not. Let's see. Doesn't seem to have a specific chatbot feature and model anymore. But just to let you know, like imagine I run a translation model. Good translation models, they're ranking most likes, I guess. Most likes the Facebook model. So for example, here is developed in 2024. Hugging Face can go explore however you want, but it's the skill set lah, that if you can write on your resume, people will be a bit more impressed with you having those practical experience lah. So if you click on how to use this model, I think you click on if you can click on I think the Google Colab. Last time don't have this they never use Google Colab to show lah. But click on Google Colab, you can figure out how to import that model lah. So it's not so complex, just how to import the model. So these models are crowd contributed lah. So you can take a look at them lah. You as usual when you run them with a GPU lah. So long story short, what I'm trying to say is that I go through a lot of things about neural networks, but not many people will make their own model lah. Most of them will import pre-trained models from a website like here. Okay, so Gwen3 Coder as well. Okay, so there are even models like I think I was using this Gwen3 to show some Gen AI course lah. But even models that can generate code as well lah. There are some down here lah. Okay, so that's a very long way of explaining to you, but not so much for me to just additional lah. The more practical side of how you actually implement these models lah. You learn the theory, yeah, you go build your model all the time. Actually, no, you may use these models, make a bit of tuning here and there lah. But don't think for tuning we are not doing for this course. Okay, but most of the tuning you must figure out on your own and learn it. Okay, learn it by yourself lah. Okay, so that's just a side note for you to take note and to try. So before we end today, let's think a bit. Let's think a bit so that you are able to retain any takeaways for today lah. Okay, so two questions for today. Two questions, MCQ questions, on contextualized embeddings as well as deep learning. So these are not multiple select. These are two questions and two answers. So try to see if you're able to answer them, because these are the core takeaways lah. Or if not, they tend to be why large language models work well. And next seminar, then we'll explain more about it. Okay, so try to see if you can answer these two questions. Okay, some responses. I see Royden has response. Kana has response. Gina also sent me directly. Chikok also sent me. Okay. Good, good, good. I think just checking if I muted myself. So okay, long story short, yeah, all of y'all seem to have gotten the response, which is contextualized embeddings are mathematical representation for same word based on its surrounding context. Okay, and then deep learning for NLP, transformers learn hierarchical patterns for long range dependencies in unstructured text. But what that means is that it's just using information from the whole sentence to make predictions. So contextualized embeddings, deep learning, they are sort of synonymous per se. So for lack of better way, or for lack of a better way of explaining for me, is that if you see the historical development, the n-grams were embeddings, you can sort of not use n-grams and embeddings to tackle your Gen AI problems or Gen AI modeling lah. You will use a deep learning solution lah. But at the same time, I added that if you are using a deep learning solution, just use a pre-trained model lah. First from Hugging Face and then use it to solve those problems instead of making your own models. But for the sake of this course, of course, most deep learning courses, then you have to train your own models So in this case, the example of CNN training that I show you in this notebook that you can test it, you can refer to. LSTM training is developing the models from scratch But of course, people develop libraries to help you to make things easier Okay, because that's the nature of computer science Most people are open source; they're very helpful to let you learn. Okay, besides that, maybe I'll just go through this case study, but I won't wait for responses There's no need to wait for responses for this because it's a bit late already. So think of it as if you want to make a smart home security system So think of it as you are safe, you are a tech startup, you're developing a new smart home security device. The engineering team divide the two specific features. One is, of course, because you want it to be secure, you want to track if somebody is able to come in. So the device, so what that could be like is the device analyzes 5 seconds of audio, and once it hears a weird audio like a window shattering, it will react Or the second feature is that the device must process when you speak to it. It says lock the front door, and then you lock the front door, do something like that, lah. Okay, so think of it. The more practical aspect, lah. I mean, this besides learning about the theory of deep learning is that imagine this is a real problem statement that you have to do, lah. So you can decide whether to use the convolutional neural network or the recurrent neural network, lah. Okay. So you can think about it. Don't need responses directly from you because it's late, but it's for you to think about it. But I think the key idea is that when you are doing any form of this audio detection or audio detection, then just think of these two ways that you can use it, the convolutional neural network and the recurrent neural network. So what you can do is that gather the data, the NLP pipeline, right? Gather the data. Then after that, process the data, use your model, the convolutional neural network, or the recurrent neural network, or any pre-trained transformer model, or any model that exists inside Hugging Face. So those are your options, lah. So just think about how you can process data and use it, lah. And then now, since I exposed you to Hugging Face and developing these models, it may not be easy for you, but now you have a semblance, an idea of how to tackle problems like this, lah. Okay, but the key thing about developing a system also is that that's why we still have three more seminars. And the last three seminars is to, of course, dive in a bit more to the LLMs, which is why LLMs are doing good. And what exactly is the pipeline for LLM, examples of LLMs as well, because I didn't really go through, I went through neural networks, but not the the complexity of LLMs. And then the next one is about evaluating models, lah. So right now, we said the RNN, we said the CNN, we say LLMs. There's so many neural networks, lah. But how do we evaluate to choose the model that is the most successful or higher probability, lah? That's seminar 5. Sorry, LLMs are seminar 4. So 2 weeks from now, evaluating models is seminar 5, which is 4 weeks from now. 3 weeks from now. 3 weeks from now. Yeah, subsequent weeks. And then the last part, the ethics of AI, lah. So a very short way for me to tell you is that if you do this whole Gen AI course, lah, and then you see it's a lot of developing models, a lot of writing code, a lot of understanding math and making decisions, right? If you want to go into a different route of not doing all these technical things, but more of the soft side, then it'll be ethical AI, lah. So ethical AI, we'll talk about the ethics of using AI, about generative AI, lah. So I mean, besides SUSS, I also do manage a course that in SP that is about ethical AI as well as data governance, lah. But that's not for me to publicize. But just to let you know that there's also a field. If you don't want to do all these calculations, you can do the ethical AI part, lah. So how you make sure that the data is governed, what policies need to come out, and what policies are useful for that, lah. Okay, so that's the last seminar, lah. So from if I'm not wrong, from here onwards, the seminars get less code heavy per se, lah, but more of cognitive understanding, lah. Okay, so thanks for spending your Friday night here. I know next week is Chinese New Year, so if you're celebrating Chinese New Year, have a early Chinese New Year. If not, have a good holiday. Yeah, so that's all for today. If you have any questions, you can stay. If not, you can always just try the notebook, lah. Yeah, try the notebook as well. So I'll see you next week for the seminar, set for the practical for the lab around the same time. And so have a good night. If anybody has any questions, I can still stay. Okay, so see you all. Okay. Okay. So rest of you do have questions, you can leave if you want to leave. Somebody else has a question on OpenAI Whisper. That's quite a new thing. Like. It's not a new thing. I've not really used this directly. Unable to detect domain was yeah. So I think there's a lot of the use case that people always ask. How can you detect a certain group, a certain groupings lah? Uh, like I assume you're trying to do some form of groupings lah, domain keywords properly lah. So you are trying to get group things using a transcription of pieces of text lah. Uh, okay. So I think generally Hugging Face tends to be the the best resource. Where's my okay? Okay, oops, where is this? Okay, so if you're trying to detect domain kind of problems, yeah, me- I have lost my chat. Okay, uh, so if you are specifically just want to target that solve that problem lah, then how come I cannot zoom up? Yeah, give me a moment. So that problem set is generally called, I think, summarization, or well, multimodal. They know multimodal as its own category. So is there a group? Summarization may be Summarization may be a model that we can solve it lah. There's one or there is a clustering lah. Generally, classification clustering. I mean, supervised unsupervised learning clustering also can lah. But example would be some summarization lah.
Sorry, maybe because I was wondering, I thought we need to like clean the text or whatever we're using before we summarize. Like currently, right, what I do is I put the audio in, then the
Uh,
model is generating into words, right? So when it does that, there's a lot of repeated words. So when I Googled, they say it's like noise. Then on top of which, I think some of the like domain keywords are being translated to like different words. So I was wondering how to change that. Like, do I use a
uh,
certain dictionary or yeah?
to clean it.
Yeah. I was thinking maybe I should clean it first before I do summarize.
So the clean it is one way to clean it is the way you use NLT NLTK stop words. It depends what is the reoccurring word lah. But so NLTK stop words here is where if you call it just now, it just removes common words lah that exist inside the English language lah. So example of common words is example of common words can't be seen here. I can print it out lah, but I can remove the this kind of common words. But if you have to, if it's very domain specific, then you may need to create the dictionary on your own to remove the words lah. So there'll be a lot of manual cleaning that you need to do lah. Yeah. Does that help you?
Yes. Generally, that should help with the summarization later, right? If let's say I see
Uh,
something really very jialat.
yeah, but you need to test it lah. So it's not like you will get the answer straight away lah. The process is quite tedious lah. You need to process. You need to have the pipeline first. Then after that you clean. Then you see if the grouping improves. If you're looking for grouping lah, you need to do it multiple times lah. So it's not so that's why people hire a computer scientist or data scientist because the process is quite iterative. You have to do it, then test to see if it works, and then do it and test to see if it works. Yeah. Yeah. So just long story short, you want to remove very common words. NLTK stop words will remove them. If not, you have to find out you have to write down your own common vocab lah. Yeah. But if you want to write down your common vocab, you can use Python code to similar to the ngrams lah, to find out the common words and see what you want to remove from that lah. So the top words, then you can reuse those words to remove from that data. Yeah. Don't know if that does that help you?
Yes, thank you.
Okay. And then if you want to split it into groups, normally you have to use a large language model. So one of the large language models, you have to test out of what kind of large language model you want to use from here. Usually, these are good enough. If not, usually supervised learning algorithms not very good. Supervised, unsupervised learning algorithms like clustering may not be as good as these models here. Yeah.
The large language model algorithm is after summarization, is it? Sorry.
Uh, it is to help you summarize lah. If that's your use case, right? Your use case is to split it into groups. Is it? Oh, no. Just donate
But
key.
use case, I'm just trying out to
Oh,
sort of
okay.
understand, yeah.
Okay. Then if you're trying out, they can try any of these models lah. So the modeling part after the processing, you can try any of these models. Yeah. So what you can do is that you can see if people have tried whatever they have tried lah. So in this Hugging Face spaces, you can also search for the use cases here lah. Yeah. Okay, you can try here lah. From here you can see how other people use AI models to develop some solutions lah. So there is some that is code detection lah. There's video generation quite expensive per se. It take a long time lah, but you can see. Okay. Yeah. Oh, maybe I should stop the recording. But you can see lah from all this lah. So Nano Banana is the Gemini's generation of videos lah. So there's a model here.
Oh,
Yeah. So you can go to Hugging Face spaces and you can see lah all the different use cases here. And I think they show you the code also lah. So you can look at these use cases as well for yourself.
okay, I think that's enough for me to explore already. Thank you.
Yeah. Okay. No worries. Okay. Amanda has a question. Are there additional reading typically required to be done in order to complete the topics? What's that other thing called? Let's stop sharing first. So for Amanda, your question is that there is the study guide, right? So the study guide, where is it? I don't really want the study guide because I'm not the one maintaining it. Yeah, but if you look at the study guide, that's when the subject slash module coordinator uh has put in more of the content. So I don't know. I can't remember where is it. As in the iSmart study guide. So that's where you need to look at for this module. So your iSmart guide, sorry, your iSmart guide. Okay, so just to help you, Amanda, in case you need some clarity, is that somewhere in one of your groups lah, you go to the iSmart guide, and then that's where there'll be more material there to help you with that lah. Okay. So I think one of your iSmart guides lah. Okay. Okay, Ken, if nobody has any more questions, then get right through this smart guide now. Okay, then there's no other material lah. Because the person that is setting your quizzes, that's all he has provided lah. So, I cannot recommend other things because it's better that you just look at the material of the person that is setting the quizzes for you lah. Yeah. But I guess you can put in the module feedback. Yeah, I mean, it doesn't help you lah, but you can put in the feedback. Yeah. After all, I think this is the second run of this course only lah. Okay. If nobody has anything else, then we will end the class for today. See you all next week.